So far, we have studied regarding flux, MMF and reluctance relation, and also we have studied how to calculate reluctance and how to calculate flux density in a given magnetic core. Now let me move to the next concept, that is force between two parallel current carrying conductors. If two conductors are carrying current through them and also placed parallel to each other, they will experience a force on them. Now the basic principle behind this is Lorentz force equation. So we have already discussed about Lorentz force equation. Whenever a current carrying conductor is placed inside a magnetic field, it will experience a force on it. And what will be the magnitude of that force? The magnitude of the force is equal to BIL sine theta, where theta is nothing but the angle between current carried by conductor and flux lines. Okay, so if the angle between these two parameters is equal to 90 degrees, then the maximum force will be equal to BIL. Okay, now we know this is the formula to be used to calculate the value, or you can say magnitude of the force. Now the next question is how to identify the direction of a force acting on the conductor. This is very important and we will study this concept in all rotating electrical machines. How to identify the direction of a force acting on a current carrying conductor due to a magnetic field. So very simple, we can identify the direction of force using Fleming's left hand rule. Okay. Very important, Fleming's left hand rule. So Fleming's left hand rule is used to identify the direction of a force, not magnitude. Magnitude can be identified using the Lorentz force equation. Direction can be identified using Fleming's left hand rule. According to Fleming's left hand rule, the first three fingers of the left hand must be placed in a mutual perpendicular direction. So you see this is a thumb, this is a point finger, and this is a central finger. And according to this rule, thumb will always represent the direction of force acting on the conductor. This is our requirement. Okay. Point finger will represent the direction of magnetic field. We know magnetic field in air gap is always from north pole to south pole. And then central finger will represent the direction of current carried by conductor. So if you know any two parameters direction, the third parameter direction we can identify. Okay, Fleming's left hand rule, thumb will represent the direction of force, point finger will represent the direction of magnetic field, central finger will represent the direction of current. Now let us practice a simple example to identify the direction of a force, and then we will come back to our concept called force between two parallel current carrying conductors. Okay. Alright. Now let me consider a simple example. Assume we have a magnetic field between a north and south poles. We know flux is always flowing from north pole to south pole. This is the direction of magnetic field. And there was a conductor in this magnetic field. Okay. Assume this circle is representing the cross section of a conductor. And this conductor is carrying current into the plane. So the cross polarity is representing the current is carried by the conductor into the plane. Now there is a current carrying conductor inside a magnetic field. Therefore, what will be the direction of force is the question. For that purpose, I am going to use left hand rule over here. Okay. See that magnetic field is moving, that is shown by the point finger, is going from north pole to south pole. Current is shown by the central finger, that is going into the plane. You see the central finger is showing the current direction, that is into the plane. Therefore, obviously my thumb is showing the direction of force, that is in downward direction. Therefore, the force experienced by this particular conductor is in downward direction. Okay, this particular force is called as electromagnetic force because it is due to the interaction between electrical current carrying conductor and magnetic field. So we will call it as electromagnetic force. Let me also take one more example. Suppose I have a magnetic field, north pole over here and south pole over here. Flux is always from north pole to south pole. Number of flux lines existed. Assume there was a conductor available in this magnetic field. This time this conductor is carrying current out of the plane. That dot polarity is representing current is out of the plane. If current is out of the plane, how to identify the direction of a force acting on that conductor? Again, left hand rule. North pole to south pole, the point finger shows the direction of magnetic field. Current is out of the plane. My central finger is showing the current out of the plane. Therefore, my thumb is going to represent the direction of force, that is showing upward direction. Therefore, the force acting on this particular conductor is in upward direction. So this is the way to identify the direction of force when you know current direction. And the same concept we will be using to identify the force acting between two parallel current carrying conductors. Okay. Now, let us consider there are two conductors parallel to each other, and this, let us assume this is conductor number 1, this is conductor number 2. My assumption is that both conductors are carrying current in the same direction. Okay, first conductor and second conductor both are carrying current in the same direction. Assume this is I1 current and this is I2 current. So whenever a conductor is carrying current through it, definitely magnetic field will be developed. How to identify the direction of flux lines when we know current direction? Right hand thumb rule. You see that current is shown by thumb, therefore my four fingers will represent the direction of flux. If you see the right side of the conductor, my four fingers are like going into the plane. Left side of the conductor, my four fingers are coming out of the plane. Therefore, the flux is into the plane over here and the flux is out of the plane over here. Mind that this is the flux developed by first conductor. Okay. Similarly, if you look at the second conductor, this is also carrying the current in the same direction, that is upward direction. My four fingers will represent the flux created by the second conductor. Right side of the conductor, it is into the plane. Look at the four fingers, into the plane. And the left side of the conductor, it is out of the plane. So this is the flux developed by second conductor. Now, if you see in between the two conductors, first conductor flux is into the plane. Second conductor flux is out of the plane. That means, can I say both fluxes are in opposite direction? Both fluxes are in opposite direction means I can assume they are demagnetizing each other. If they are demagnetizing each other, resultant flux becomes very, very low over here. I can say it is weak magnetic field. Okay. Why it is very weak? The reason is both are demagnetizing each other. Therefore, compared to this medium, outside medium will have a strong magnetic field. All right. Right. So this region and this region will have a strong magnetic field. Between the two conductors, the magnetic field is very weak. The reason is both are demagnetizing. Okay. Now, to identify the direction of force acting on the conductor, I will take this strong magnetic field as reference so that we can easily identify the direction of force. As I already explained how to identify the direction of force by using Fleming's left hand rule. If I use Fleming's left hand rule, you see the first conductor, current direction is shown by central finger of the left hand, that is in upward direction. You see the strong magnetic field that is out of the plane. You see this, my point finger is showing out of the plane, that is the magnetic field. Current is in upward direction, that is shown by central finger. So what my thumb is going to represent, the force that is in this direction. Okay. So this is the force on this conductor. Similarly, you look at this conductor, current is in upward direction. You see my central finger is showing upward direction, but magnetic field is into the plane. This is a strong magnetic field into the plane. Look at my left finger. So current is in upward direction, that is the central finger. Magnetic field is into the plane, that is the point finger. So what my thumb is representing, the direction of force. Therefore, this is the direction of force. Now, if you look at both forces together, can I say these two forces are definitely pushing the two conductors towards each other? Pushing the two conductors towards each other, that is nothing but attractive force. Okay, so therefore, when two conductors are carrying current in same direction, both conductors will experience force of attraction. Okay. In the same way, we can study the concept if the two conductors are carrying current in opposite direction, what will be the nature of the force? Okay, see this. Assume these are the two conductors we have. First conductor is carrying the current in upward direction. Assume this is I1 magnitude. I am assuming second conductor is carrying current in downward direction. This is I2 magnitude. So both conductors are now carrying currents in opposite direction. So identify the respective magnetic field. Current is in upward direction. So here magnetic field is into the plane. Here it is out of the plane. So we have flux into the plane and flux out of the plane. This is the flux developed by first conductor. Similarly, second conductor is carrying the current in the downward direction. If it is carrying the current in downward direction, here the magnetic field is into the plane and this side the flux magnetic field is out of the plane. So here the flux is into the plane and here out of the plane. So therefore, if you see the region between these two conductors, both fluxes are coming out of the plane. Both are coming out of the plane means both are in same direction. Both fluxes are in same direction means I can say both are magnetizing each other. Therefore, we can observe a strong magnetic field over here. Therefore, compared to outside, the inside magnetic field, or you can say the field between the two conductors is more stronger. Now I will consider this stronger magnetic field as reference and I can identify the direction of force acting on each conductor. How to identify the force direction acting on each conductor? Fleming's left hand rule. Let me quickly go through it. So see that first conductor, current is in upward direction. So my central finger is showing in upward direction. The strong magnetic field is into the plane. Look at my point finger is showing into the plane. Current that is in upward direction, central finger. So my thumb is showing the direction of force acting on this conductor. So this is the direction of force. Okay. Similarly, coming to the second conductor, current is in downward direction. Look at my central finger, that is in downward direction. Magnetic field, the strong magnetic field is into the plane. This is into the plane. Therefore, my thumb is showing the direction of force that is in this direction. So the force is in this direction. Now, if you observe these two forces, can I say both forces are in opposite direction? That means indirectly the two conductors are pulling away from each other. Therefore, it is a repulsive force. This is repulsion. So, conclusion is when two conductors are carrying current in same direction, there is an attractive force. If they are carrying current in opposite direction, they are experiencing repulsive force. Now, our next concept is how to calculate the magnitude of that force, okay, using Lorentz force equation. Now, let us see how to calculate the magnitude of the force experienced by a current carrying conductor. According to Lorentz force equation, the magnitude of the force is equal to flux density into current into length of the conductor. I am assuming the angle between these two is equal to 90 degrees. Now, the point here is that to calculate the magnitude of force, first we have to calculate the magnitude of flux density. We know flux density can be written as mu into h. So, if I know what is the intensity of the field experienced by the conductor, then obviously density can be calculated so that we can get the magnitude of force. So our first discussion is calculation of field intensity H. Okay, calculation of H. So I'll use a standard formula to calculate H by a current carrying conductor. You see that. Assume I have a conductor with me carrying a current magnitude I. Based on the direction of current, I can understand the flux lines will be along my four fingers. Okay, so the direction of a flux will be like this. This is how flux lines are going to be created. All right. Now, from this conductor, let us assume there was a distance called d. Okay. And I wanted to know what is the value of h at this particular point. Okay. At this particular point, which is d meters away from this conductor, what is the value of field intensity h? So the standard formula for this field intensity h is equal to current carried by the conductor divided by 2 pi d. Okay, where d is the right angular distance between the conductor to this particular point. So if you know the field intensity h, then we can calculate the magnitude of a force at this particular point if there is any current carrying conductor. Okay. So very important, let us use this h value to calculate the force experienced by current carrying conductor. Okay, let's see. Now let's see that. Assume that there are two conductors which are parallel to each other. This is conductor number 1, this is conductor number 2. The distance between these two conductors is equal to, let us say, d meters. Conductor 1 is carrying a current I1, conductor 2 is carrying a current I2. So now what my question is, we have already studied if the two conductors are carrying current in same direction, there will be a force of attraction, and I wanted to calculate the magnitude of that force. So the first question is force experienced by okay. The first question is force experienced by conductor number 2 due to the flux produced by conductor number 1. Later we will see force experienced by conductor 1 due to the flux created by conductor 2. Now you see here, I wanted to calculate how much force is acting on conductor 2 due to the flux created by conductor 1. That means it is the interaction between flux created by conductor number 1 and current carried by conductor number 2. Okay, the interaction between these two parameters will create the force. So therefore the force experienced by conductor number 2 is nothing but the interaction between flux created by conductor number 1 and current carried by conductor number 2 and length of conductor number 2. Okay, what is the formula for flux density? Mu into h of conductor 1, I2 into L2. We have already, mu can be written as mu naught into mu r. We have already discussed about formula for h. See here, conductor 2 is exactly d meters away from conductor 1. So therefore h is equal to I1 by 2 pi d. So why I am using I1 here? Because this h is created by first conductor into I2 into length of conductor number 2. Suppose if the medium between these two conductors is air, relative permeability will be equal to 1, then the force will be mu naught into I1 I2 by 2 pi d into length of conductor number 2. So this is the force experienced by conductor number 2 due to the field created by conductor number 1. In a similar fashion, we can calculate force experienced by conductor number 1 due to the flux produced by conductor number 2. Okay, let me do the calculation here itself. Now let's see, force experienced by conductor number 1 due to the flux created by conductor number 2. That means it is the interaction between flux created by conductor number 2 and current carried by conductor number 1. So therefore, the magnitude of the force experienced by conductor 1 is equal to B2 into I1 into L1. The conductor 1 is experiencing force because of the field created by conductor number 2. How can you write B? B is equal to mu into H2 into I1 into L1. We know already formula for H. Mu is equal to mu naught into mu R. H2 is nothing but I2 by 2 pi d into I1 into L1. So if the medium is air between the two conductors, mu R is equal to 1. Therefore, it is mu naught into I1 I2 by 2 pi d into L1. This is the force experienced by conductor 1 due to the field created by conductor number 2. Now you understand one point. First of all, these two conductors are carrying current in same direction. Therefore, there will be an attractive force between these two. Am I right? So this is the force experienced by conductor 1. This is the force experienced by conductor 2. And the magnitude of these two forces also we derived. And you imagine here, suppose if I ask you a question. If the distance between these two conductors is reduced, what happens to the force? Okay. From the formulas you can understand, if the distance between the two conductors decreases, definitely the force experienced by the two conductors also increase. Okay. So when two conductors are very close to each other, there is more force of attraction. When the two conductors are far away from each other, very less attraction will be available. And also you see that the magnitude of the force also depends upon permeability. If the medium is highly permeable, you can expect more force of attraction. If air is the medium, definitely permeability is less, therefore the force of attraction is also less. And a few more conclusions are, force is also directly proportional to product of the current carried by these two conductors. That means if the magnitude of the current increases, the magnitude of force between the two conductors also increases. Okay. So force is proportional to permeability, proportional to the currents carried by conductors, but inversely proportional to the distance between the two conductors. Okay. Now let us try to solve an example question based on the concept that we discussed. Let me read the question. Two long parallel conductors are laid at a center to center distance of 2 meters. So it was given the distance between the two conductors is 2 meters. In air medium, that means relative permeability is equal to 1. Each conductor is carrying 1000 amperes current. The current carried by each conductor is 1000 amperes in opposite direction. So if conductors are carrying current in opposite direction, they will experience a force of repulsion, right? The length of each conductor is 100 meters. Okay, length of each conductor is 100 meters. The force experienced by each conductor is how much is the question. Just now we discussed the force experienced by each conductor in air medium if they are carrying current through them. The same formula I will use so that I can calculate the magnitude of force. Okay, so see this. Now important thing is both conductors are carrying same current and having same length. As they are having same length, obviously they will experience the same magnitude of force. Okay, so therefore force experienced by each conductor, same formula. Mu naught into I1 I2 by 2 pi d into length of the conductor. We know value of mu naught is 4 pi into 10 power minus 7 into both are carrying 1000 amperes current. 1000 amperes current by 2 pi into the distance between the two conductors is 2 meters into length of the conductor is 100 meters. Okay, all are in meters. Now if you solve this entire equation, let me show you the magnitude. It will be 10 newtons. Okay, that is the force experienced by each conductor. Okay, so as the length of each conductor is the same, therefore they are experiencing same magnitude of force. Now in this example, let me read the problem. two long parallel conductors A and B separated by a distance of 20 centimeters. The distance between the two conductors is 20 centimeters. Carrying currents 500 amperes by one conductor, 600 amperes by another conductor, respectively in opposite direction. The flux density at the midpoint perpendicular to each wire is how much? Okay, that means indirectly, see, there are two conductors A and B. First conductor, let us say it is carrying current IA. Second conductor is carrying current IB. Both are carrying currents in opposite direction. That was given in the problem already. Now, according to the current direction, you try to identify the direction of a flux using right hand thumb rule. If this is the current direction, my four fingers will represent the flux direction. So here the flux is into the plane, it is out of the plane here. According to the current direction, downward direction, here the flux is into the plane and here it is out of the plane. Therefore, if you see between the two conductors, both fluxes are in the same direction. That means both are magnetizing each other. Okay, that means the flux densities will aid. And also the question here is that the value of the flux density at the midpoint between the two conductors. Okay, between the two conductors at midpoint we need to calculate flux density. So that means this is A and this is B. The distance between the two conductors is equal to how much? It was given in the problem, 20 centimeters. But we are asked to find out flux density at the midpoint. Therefore, this is 10 centimeters and this is another 10 centimeters. At this midpoint, we have to calculate the total flux density. First of all, at this point, calculate the flux density by conductor 1. Similarly, calculate the flux density by conductor 2. Add both of them because both are magnetizing. Then you will get the total flux density. Okay. So therefore, the total flux density is equal to density due to conductor A plus density due to conductor B. What is the formula for flux density? That is mu into HA plus mu into HB. You can take mu common. What is the formula for HA? We already studied. Current carried by conductor A by 2 pi into, you should not use the total distance D because we have to calculate at the midpoint, the distance is 10 centimeters. 2 pi into 10 centimeters plus current carried by conductor B by 2 pi into same 10 centimeters. Okay, why I am adding both flux densities? Because both magnetic fields are aiding each other. So mu is equal to mu naught into the medium is air, so relative permeability is 1. Conductor 1 is carrying 500 amperes by 2 pi into 10 centimeters. Conductor 2 is carrying 600 amperes by 2 pi into 10 centimeters. Okay, mu naught you substitute 4 pi into 10 power minus 7. The overall calculation will be 0.0022 Tesla. Okay, that is the final calculation. So my suggestion is please complete the calculation, then you will get this answer.